This is the conversation with Andrew Knoll. He's the Fisher Professor of Natural History at Harvard University, the author of acclaimed books like Life on a Young Planet and A Brief History of Earth, and one of the leading academics in the fields of the early evolution of life and Earth's environmental history. In this conversation, we discuss his journey falling in love with these subjects, the interdisciplinary nature of these fields. We talk about the origins of Earth, the different epochs, what evidence we have for each, how we can measure it. We also talk about the origins of life on Mars, and then the future of this planet. This is no time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, rate 5 stars in Apple Podcasts. This project takes a lot of my time, money, and efforts. If you'd like to see it continue, please consider making a donation on Patreon or Anchor. You can join as a member on YouTube. You can buy gifts on Instagram Reels, or you can buy super thanks on YouTube. If not through monetary channels, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For other forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. You grew up in West Reading, Pennsylvania, in the middle of the Pennsylvania Dutch country. And you've said in the past that at that age, there were only 3 major professions in your purview: becoming a doctor, becoming a lawyer, becoming an engineer. And because you were good at math, you ended up enrolling in engineering. And when you were in college, you quickly found out that engineering didn't spark your interest as much. So you ended up auditing a lot of science courses, including one in the earth sciences and biology. And then one night in your dorm room, you had this light bulb moment that these sciences are being treated as different worlds, but they really need to come together. So let's start here. What did you see in that moment? What patterns emerged to you? What was the magic, the power of earth sciences, biology, geology, paleontology that appealed to you so strongly at that age and made you want to bring them together?
Well, I think I was just fascinated by the material. I mean, I had some biology in high school, but not very deep, and really had not a great deal of information about the earth sciences. So I was excited when I took a geology course that the rocks that we see around us contain a history. They're basically Earth's history books. And since I had been, as a boy, interested in history and archaeology, for the very reason that, our story is written in things that are beneath our feet if we know how to look for them, I got excited by the fact that I could learn about biological history by looking at that geological record, at the fossils, but also the rocks contain information on environment at the time and place those rocks formed. So you have this whole, ecosystem preserved that goes well back into the distant past of our planet. And I just thought that was the most interesting thing I could imagine. And the fact that you couldn't do it just learning geology and you couldn't do it just learning biology, that you had to learn the two and try to integrate them. I thought that was just a very enjoyable challenge. And so once the idea got in my mind, I never stopped.
I have 2 follow-up questions for you about that moment. The first is about this light bulb moment that you had in your dorm room. In the essay, The Triumph of the Naturalist, your former colleague at Harvard, Stephen Jay Gould, mentioned that many people believe that academic research is like a Sherlock Holmes mystery, that it's set up like this incremental logical steps. And if you apply reasoning and deduction at each step, you'll progress to the next level. But he had said that for him, that style never worked. He preferred the style of Lord Peter Wimsey, where he took a more integrative approach, where he exposed himself to all the facts. And for a while, nothing made sense. And then suddenly everything snapped into place and things made sense. There's a light bulb moment. Where do you stand on this? Because in your books, in your previous interviews, you've often said, you just mentioned as well, that in a way, geology is reading Earth's history book. When you visit the highlands of Spitsbergen, or you visit the Grand Canyon, or the Rhynie Chert, or the Burgess Shale, you're reading pages of the history book. So in a way, in geology, you can actually solve the mystery in incremental steps because it's arranged as layers and you can make those logical deductions. So do you get the feeling that in your work and in geology as well, you can solve it like a Sherlock Holmes mystery and just take logical steps? Or do you resonate with Stephen Jay Gould that for a long time, nothing makes sense and then everything clicks and falls into place?
Yeah, I should say to start off with is that's one of my favorite essays that Steve wrote. And I think, not surprisingly, there's a multitude of intermediates. I agree with Steve that we don't all go around and logically deduce everything because once you have all the facts, it inevitably leads you in the right direction. And there have been moments in my life where things that I'd puzzled over for many months all of a sudden seem clear for who knows what reasons. But having said that, I think we do go logically to a certain extent through the rocks. There are ways of interpreting the physical and chemical features of rocks, and those lead us to certain conclusions about an environmental history. We find fossils, and if you know something about biology, you can make some sometimes very strong inferences about life at that time. But that said, every once in a while, you start just thinking in a new direction. And it is kind of Peter Wimsey-like in that it's not like you gradually build up to it. In my own case, one of my favorite examples is I'd gotten interested in the geological record at the time of Earth's greatest extinction, 252 million years ago at the end of the Permian period. And with my friend and longtime field partner, John Grotzinger, we started getting interested in why does the geological record in the immediate aftermath of this extinction look like the geologic record of the early Earth? And that led us to certain environmental conclusions. And then again, I think it was just one night, and not when I was particularly working on it, but it came to me that the geologic record seemed to be telling us that there was a big increase in carbon dioxide in the atmosphere, which we now know was because of massive volcanic eruptions in what's now Russia. And then just armed with that, I thought, well, what does that mean for biology? And then you go back into Sherlock Holmes mode in that my friend Dick Bombach and I spent literally several months just in the library reading hundreds of papers on the physiology of carbon dioxide and how it affects different organisms. And what became clear is that some organisms are very vulnerable to changes associated with increasing CO2. Some are very resistant. And when we sort of divided these up into different camps, they turned out to be very good predictors of what went extinct and what survived. So yeah, I guess I would say that at least in my life, and I think in the lives of many scientists, it is part Sherlock Holmes and part Peter Wimsey. It's not all one or the other.
It's so interesting to me because when I've spoken to musicians, poets, actors, they talk about this inspiration that just strikes them from somewhere and then they try to explore it. And I'm surprised to find how many researchers as well have that same stroke of inspiration and then take that forward. You would assume that science is just empirical, is always based on deduction, reasoning, but there is that light bulb moment that drives it. A second follow-up, and you mentioned you can't just read Earth's history book by just learning geology or biology in separate chambers. And that's why you want to bring these worlds together. These interdisciplinary links sound great to me in theory, but I just feel it's such a Herculean task that's getting tougher and tougher over time. I've interviewed quite a few professors of philosophy on the show, and especially ones who work in philosophy of physics and philosophy of math. And they've lamented the fact that these subjects have become so vast now that in a way, the foundational questions of physics and math have been relegated to the philosophy department, or so to speak, because, and they say it's inevitable because these subjects have become so big, so broad and deep. There's so much information out there that there are subdivisions within each subject that a researcher could spend their entire life in just one subdivision and barely make a difference.
that they're not able to work in multiple different worlds at the same time and see the links between them. This is giving rise to a lot of inconsistencies, especially in physics. You have the Copenhagen interpretation of quantum physics, or even in math, like the Russell's paradox. Do you think this is also a challenge now in geology and evolutionary biology? These fields are becoming bigger and bigger exponentially, becoming so vast. There's so much more information that we're finding out every single day. Is it now becoming tougher to find people who can dabble in multiple different worlds, to have these polymaths like we had in like Isaac Newton or Galileo or Aristotle? Is it tougher to find people who can now dabble in all these worlds, find the links, and bring these worlds together?
I think on the contrary, I think that science is rapidly becoming more interdisciplinary.
Okay.
For the simple reason that if you want to solve tough problems, you'll never understand climate and climate change unless you can draw inferences from both the earth sciences and biological sciences. And I think that's true of many fields. So yeah, it takes some work. But I should say too that, I wasn't the first person ever to think about this. Alexander von Humboldt in the early 1800s made it very clear in his writings that you couldn't understand the mountains and the plants on them independently of each other. And people have come, beginning of the 20th century, people started talking about this. In fact, the field actually has a name now. It's called geobiology. And it's actually becoming more and more highly populated because young scientists see the advantages of being able to draw from both fields.
Let's start diving into one of these fields. You are the author of A Brief History of Earth, 4 billion years in 8 chapters. So you're clearly an expert at summarizing massive timescales into really short, concise answers. So I'm going to ask you to flex that skill one more time. This is an unfair question, but can you provide a brief history of Earth? How did Earth originate? How did we get from that to present day? What were the major epochs or the eons in the middle? What were the key features of each eon? How did we go from one eon to the next?
Okay, the first thing to know is that the Earth did not always look the way it does now. It's not even clear that the Earth that we see around us is representative of the Earth through Earth history. It is an end member in many ways. And we'll walk us through some of those changes. But to get to your first question, that the Earth originated along with the rest of the solar system about 4.5 billion years ago, when dust and ice started to collide and build into ever bigger structures. And we ended up with, a small number of planets, but also we ended up with a lot of debris from these early moments in the solar system's creation. We call them asteroids when we see them in space, and meteorites when we find that they've bumped into the Earth. And if you ask, how do we know that the Earth is 4.5 billion years old? Well, the answer is that there is uranium in some of the minerals in these early remnants of solar system formation. Uranium is great because it has so-called radioactive isotopes, which is types of uranium that actually decay to lead on timescales that we understand. And they tell us that the solar system came together on this 4.5 billion year old timescale. Now, interestingly, we don't have any rocks on Earth, at least that formed on Earth, until about 4 billion years ago, because not only does our planet record its own history in rocks, but it erases that history with a number of processes too. And so the first 500 million years of Earth history is more or less the dark ages. As I talk about in my book, there are certainly minerals that come from those early time periods, and they tell us something about the early Earth. But it's really about 4 billion years ago that a rock record starts to be something we can look at. And so if you look at what's called the Archean eon, from about 3.8 to or maybe about 4 billion years ago until 2.5 billion years ago, that's sort of the early history, the Stone Age, if you will, of the planet. And it's an Earth without measurable amounts of oxygen gas, so you and I wouldn't last very long on that planet. It's an Earth in which there was only limited exposure of continental masses above sea level. It was more or less a water world in those days. So it's a very different world. But the other thing we know about that world from the geologic record is life existed. And again, it wasn't mammals or dinosaurs. It was microbial. It was bacteria. And we know that photosynthesis existed way back then. So all the makings of ecosystems on Earth where different organisms cycle carbon and sulfur and nitrogen, the other biologically important elements through the system, that system was put in place in this microbial world of the early Earth. And to be honest, to this day, the biological world would be just fine without plants and animals, but it can't exist without these bacteria. They're the basic building blocks of ecosystems on Earth, and they evolved very early on this alien planet. Now, we move to what's called the Proterozoic eon about 2.5 billion years ago, and that will last until about 540 million years ago. It's a long period of Earth's middle age, and that begins and ends with very important changes. About 2.4 billion years ago, the geologic record tells us that oxygen gas is starting to accumulate in the atmosphere and surface oceans. Not a lot. It didn't make it a modern world in terms of atmospheric composition, but enough oxygen that organisms could start to use it for things like respiration, what you and I do when we eat something and then derive energy from it. Again, we know that the source of the oxygen was photosynthesis, so you need a biological component. But this happens at a time when continents are emerging and to form, large continental masses and mountains. And those are now increasing the amounts of nutrients coming into the system. So the way I see it is that it's a combination of biological processes and physical processes that together really transform the Earth into one that has oxygen. And that begins Earth's middle age. And it's sometimes been called the boring billion. But in fact, it is a time of prolonged warm climates, not much oxygen, certainly no oxygen in the deep ocean. The deep ocean was actually rich in iron in those days. But again, at this point, by about 1,700 million years ago, we have evidence that not only are there bacteria, but there's a new type of cell called the eukaryotic cell, cells that have a membrane-bounded nucleus and other features, the cells that make up our own bodies, for example. So the world is changing. And then toward the end of this eon, it changes again. We start having more oxygen. We have major ice ages. And amid all of this, for the first time, we see fossils of animals. So the Earth has now entered a new state called the Phanerozoic eon, the age of visible animals. And that's when a more familiar Earth history begins, that there are fossils of various types. We have evidence of ice ages, of mass extinctions, eventually leading to our own lineage, and really only in the last, blink of an eyelash, as far as Earth history is concerned, to technological humans that themselves are capable of changing the planet. So to put it all in perspective, when you go to a museum, you'll often see fossils, and they're fossils of animals and maybe plants, but those only really record the last 15% of our planet's history. Most of Earth history is microbial, and most of it is in a world that's physically very different from today.
Firstly, I think this is a fantastic overview. You really have a knack for being able to summarize these massive timescales really in such a beautiful fashion. When you talk about these eons changing from one to the next, how do these changes occur? Are there singular events that cause that change, let's say an asteroid impact or a supervolcano eruption? Or do you get the feeling that it was eventual, like once you went to the first eon, it was only bound to then lead to the next one, that there were natural processes that were being followed?
Well, that's been argued by some people. And because if you start with a world without any oxygen, getting oxygen is one direction you can go in. Of course, it's not obvious that Earth never ever needed to become oxygen rich. Certainly, that's a function in part of biology. But what I would say is the biggest major changes that I outlined, from the primitive Earth to the Middle Age Earth to the more modern Earth, we are seeing tectonic, that is, physical Earth processes pushing more biological activities. And together then, they not only change the environment, but they change it in ways that make new types of biology possible. So again, I would say that in order to understand how our planet has transited from one state to another, you have to bring biology and earth science together.
I want to take a small digression because you brought up uranium and how it's embedded in zircons and how that can be used for dating Earth history. There's another method that you use, which is carbon dating. So I want to touch upon the science of carbon dating as well. What is carbon dating and how do you use that for dating a rock?
Okay, well, it all goes back to the same principle, and that is that most elements have several different forms called isotopes. So carbon, 98% of all the carbon, 99% really of all the carbon on this planet has 6 protons and 6 neutrons. So it has a molecular weight or an elemental weight of 12. But about 1% has an extra neutron, so carbon-13. And parts per trillion have 2 neutrons, so it's carbon-14. And carbon-14, unlike 12 and 13, is radioactive. That is, it will decay to nitrogen. The half-life is something like 5,700 years or something like this. So what you can do is take things like wood, for example, that has a certain amount of carbon-14 in it as it forms. And then once that wood gets buried, let's say in a landslide or something, the clock starts ticking. And you can then, using a mass spectrometer, you can actually determine, how much C14 there was and how much is left. And that gives you dates. And so carbon-14, because it's so-called half-life, that is the time it takes to lose half of the original amount, that's so short that it's something that's very useful on archaeological timescales. If you want to know the age of early dynastic Egypt, that's your friend. If you want to know what happened billions of years ago, uranium is your best friend. In part because there are 2 different isotopes of uranium that both break down to form different isotopes of lead, and they do it at different rates. So you essentially get 2 clocks. And that allows you to tell whether one or both of those clocks have been altered by later geologic processes. So uranium lead dating that has really been one of the major tools that has allowed us to take this relative history of the Earth and convert it into something that we can talk about in terms of years.
I love it. Nature's amazing that we have so many different types of clocks, natural clocks that exist in these elements. I took this digression. We were talking about the nature of these transitions and whether some people have argued whether it was eventual or whether it was a singular event that caused it. I want to take a philosophical tangent. It's in my nature, unfortunately, so I have to do this. In your book, Life on a Young Planet, you quote a verse from T.S. Eliot's Little Gidding, where he says, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time." In your book, A Brief History of Earth, you say, if you look closely at imposing peaks in the Rocky Mountains or the Alps, another aspect of Earth history may snap into focus. Their tooth-like shapes don't reflect deposition. On the contrary, they are being sculpted by erosion, physical and chemical processes that wear away rocks, eradicating their stories. Earth writes its history with one hand and erases it with the other. And as we go further back in time, erasure gains the upper hand. One thing that struck me when I read both your books was that it seems like there's a cyclical nature that's intrinsic in the universe and in all the processes on Earth. It's everywhere. You spoke about carbon levels, and when carbon levels were high, that led to the rise of plants and photosynthesis. That led to the great oxygenation. That led to the rise of aerobic bacteria, animals, and ultimately humans. Your fellow grad student, Jack Sepkoski, also discovered a similar cycle in biological diversity, that when there's an extremely high point in diversity, it's followed by a massive extinction, and then it rises up again. There's a cycle there as well. Supervolcanoes have another cycle. There's stagnancy, then an eruption. If I have to extract a high-level cosmological purpose for the universe or Earth, do you think it would be fair to say that it seems like there's a cosmological purpose for the universe to increase entropy? Every time there's an extreme, and it seems like we're stabilizing at one extreme, there's a regression to the mean, and then we go down to the opposite extreme, and we seem to be in this infinite cycle of ebbs and flows.
Well, yeah, again, there are people who are, even as we're speaking, are writing books and papers about entropy as the fundamental way of thinking about particularly biology on the planet.
Mm-hmm.
I must say that kind of thinking is above my pay grade. So I'm interested in what happened. So, for example, as Jack Sepkoski pointed out, when he took several years and just tabulated the number of different kinds of fossils in rocks of various ages, that there have been several times in the age of animals when diversity's collapsed, what we call mass extinctions. And again, those have increasingly clear causes. In the case of this extinction that I worked on at the end of the Permian, it's volcanism 1 million times larger than anything you'll ever see in your lifetime. If it's extinction 66 million years ago when the dinosaurs disappeared, that appears to have been caused by a large meteorite that hit the planet. So again, whether you have the extinctions because diversity was high is not clear, but what is very clear is that in the age of animals, there are physical processes that really countermand the slow march forward of organisms, and those are very much an important shaping element. The reason we see the animals we do around us today has as much to do with extinction as it does with evolution, other evolutionary processes.
If I could channel the argument for those who make the case that the cosmological purpose is to increase entropy, would it be a stretch to say that humans seem to be the universe's answer towards how plants are storing carbon and it was not being released in the atmosphere, that humans came along and started burning trees, conducting deforestation, releasing that carbon back in the atmosphere?
Yeah, whether they're fulfilling some higher cosmological purpose is not obvious to me. I have a friend named Paul Falkowski, who's a very, very good biogeochemist, and he talks about the modern as being the credit card state of the Earth, in that, in a sense, we have been spending Earth's accumulated energy in the forms of fossil fuels, and we're going to pay for it later. And so, again, I'm agnostic as to whether there really is something meaningful about purpose to talk to, but there are those who think there is.
Let's zoom in the Archean era, which is the first point where the microbial life started to emerge. All the way up till the mid-20th century, we used to believe that it was relatively difficult for life to emerge, that it was a chance event of sorts, until 1952, when Stanley Miller and Harold Urey conducted the Miller-Urey experiments, where they simulated Earth-like conditions in a test tube, ran electric sparks through it, and immediately they discovered the presence of organic molecules, thereby implying that if you have Earth-like conditions, it's relatively easier for life to emerge. So let's pause here. How does life emerge if you have those Earth-like conditions? And then, do you agree with this conclusion I've drawn, that if you have Earth-like conditions, then it'll be quite easy for life to emerge?
Yeah, everyone has an opinion on that. And it turns out that, when you look around, you see the only instance of life that we know about in the universe. Now, it's interesting that just within the past 2 weeks, a survey was published among scientists as to Do they think it's probable or improbable that life exists elsewhere? Yeah. And, something like 85 or 90% of scientists saying, yeah, it's probably there somewhere. Now, the problem, of course, is detection, not speculation. But I do agree with Stanley Miller, who I think I wrote about this once, that I was once at a meeting that Stanley was at, and somebody asked him how long it took for life to begin. And Stanley thinks for a minute, and then he says, I think a decade's too short. And he says, and maybe a century is too short, but if you can't do it in a million years, you probably can't do it. And that really encapsulates this view that if you have the right environmental conditions, then they will give rise to self-replicating, evolvable systems that we call life. And since this epical Miller-Urey experiment, there have been thousands of experiments being done, an increasing number in the last decade. And they do seem to tell you that, yes, under plausible early Earth conditions, which would include, this is interesting. There's one school that says, well, you want to do this in lakes because wetting and drying is important, and you have a number of chemical conditions in lakes that would be great. Others say, no, it's deep sea hydrothermal vents because you have a series of conditions that are good as well. And I like to remind both camps that if you go to Iceland today, you find lakes sitting atop mid-ocean ridges, hydrothermal ridges. So in places like Iceland, before there was life, you probably had conditions that would give rise to things like amino acids, the building blocks of proteins, nucleotides, the building blocks of nucleic acids. And again, there's been experiments that show how those can link up to make something functional. And in particular, that you can have selection, like natural selection, on molecules that do certain things like replicate faster or with more fidelity. So broadly speaking, I think we've learned enough since Stanley's experiment to think that, yes, there are many ways of getting to the molecules that make up life, and that it might be that under many conditions, some of those will emerge as self-replicating and evolving systems. Now, it has to be said that when we look around our own solar system, there are a number of meteorites that are actually rich in amino acids and things like this. And those, a lot of people say, well, they're telling us that the materials of life came in from outer space. I think what they're really telling us is that maybe it's not that uncommon to have the conditions where you can make things that could come together and form life. So I think we've learned a lot. There's still a lot we don't know. I don't want to oversell the state of our knowledge. But the problem really now for life in the universe becomes one of detection. I'm fond of saying that in our own solar system, we can go to other planetary bodies and moons and asteroids and that, and actually look for evidence of past or present life. In our, larger cosmological neighborhood, we can start looking at extrasolar planets, which, when I was in graduate school, none were known. Now it's thousands are known, and they're being discovered on a regular basis. And some of them we now have the ability from some very, very clever engineering to actually make inferences about atmospheres of these extrasolar planets. And so that might allow us to have some inferences about life, nothing yet. But, for the most of the universe, it's too far away for that to work. So for most of the universe, the only way I think we'll ever know about life out there is if they call us up and tell us. So again, it's the difference between logic that tells us, yeah, it could be fairly common given the billions of stars with most of those systems have planets associated with them. Yeah, whatever happened here may well have happened in another place. Demonstrating it is hard.
I get the feeling that what this experiment did successfully was bifurcate the question about the origin of life and say, yes, it can be relatively easy for life to begin, to originate, but persistence of life is a question we haven't solved yet, right? So it's quite possible the organic molecules will develop, or how it would evolve over time and whether it would persist is now a separate question that's evolved out of that finding.
Yeah, I would agree with that. In fact, I increasingly like to emphasize that what might be unusual about Earth is not so much that life began, but that it has persisted for 4 billion years. That may be rare. Again, we don't really know, but all of the vicissitudes of Earth's physical history that we talked about a little while ago allowed life to persist. And, 4 billion years after it starts, we get things that have technology and are capable of sending signatures into space, and for better or for worse, are capable of changing the planet around them.
Let's explore this. You brought it up. You opened up this can of worms, so we'll go there. You said this might be a rare occurrence, this supposed rare Earth hypothesis that it is just one giant sequence of miraculous events, one giant fluke, one after the other, whether Earth was in the Goldilocks zone of the sun, whether it was next to a gas giant like Jupiter that was attracting all the asteroids away. We didn't have any supervolcano eruptions for a long time. High amount of carbon and nitrogen in the beginning led to a greenhouse effect. That helped the prebiotic reactions, then the oxygenation. This seems like one fluke after the other. Do you think, Stephen Jay Gould used to talk about the role of serendipity in evolutionary history as well. So do you think this is just one giant fluke, the biggest chance occurrence in the world possible, or life just adapts to whatever hand it was dealt? So these are the conditions on Earth. Life just adapted to evolve whatever conditions presented to it. So if in any of these steps something was different, let's say we didn't go through the great oxygenation event, then life would have just adapted like plants did. And intelligent life would have been some form of plants. It would just take in whatever conditions were given to it and adapted to that.
Yeah, I think there are lots of intermediates between the two end members that you suggested. And even if life is a fluke, then statistics comes into the discussion. So, you might say, well, the chances of giving rise to persistent life on Earth are 1 in a million. And that may not be a bad number. We don't know. But then you say, well, look, there's actually probably billions of galaxies, each with billions of stars, each with multiple planets, or most of them with multiple planets. So if the chances of life originating and persisting on a planet or a moon are 1 in a million, there must be millions or billions of life forms that have, at least in the history of the universe, existed. So I don't know that it gets us that far to take the fluke hypothesis and just beat it to death. Although I think it is important to think that how a planet itself changes through time is important. And there you can just take my second favorite planet, which is Mars. And, if you look at the ancient geologic record of Mars, Mars at one time had, for reasonable lengths of time, persistent liquid water, things like this. We don't know whether life ever evolved there or not, but Mars and Earth have had different trajectories in their planetary histories. Mars fairly early on lost this persistent water and became the kind of cold, dry planet that it is today. So in the difference between Earth and Mars then, at least in part, is the difference between the trajectories of planetary history. And again, that's something that bears thinking about too, particularly for this question of persistence.
How do we know that Mars had water? What evidence did we find? What measurements did we make? And then how do we know that, or do we have any information on why it lost its water?
Well, that's a good question. One of the things, again, if we look at ancient rocks on Earth, there are physical features of rocks, things like ripples that you see, if you go to the beach, and things like cross bedding, where you have beds aren't, strictly parallel to the surface, that tell us, in some cases, about waterborne movement of particles. And we see those in ancient Martian sedimentary rocks. We also see evidence of water in minerals. So if you look at gypsum, for example, gypsum is calcium sulfate, but it also has water molecules. So if you see gypsum on Mars, there was water there when those things formed. And so both chemical and physical information tells us that there have been times in Mars's fairly early history when there do seem to have been fairly widespread lakes. It's been argued there could have even been an ocean in the northern hemisphere. But the other thing that interests me is that people rightly say, well, these persisted for long periods of time, maybe tens or hundreds of thousands of years. But, given that we're talking about an interval that's, 1 billion years long, it may be that early Mars was episodically warm and wet. And my friend and colleague, Robin Wordsworth, and I have explored that a little bit. I say we, but Robin did all the modeling. But I think we agree that Mars may well have been episodically wet, that when you have either massive volcanism or a major meteorite impact, that can transiently change the planet so it becomes warm. You get liquid water, but then things cool off, quiet down, the water leaves. So to me, what it looks like is that early Mars certainly had intervals of time that were relatively warm and wet, but those intervals have become fewer and fewer through time. And it may well be that even by the time we first start seeing evidence of life on Earth, Mars was going out the other end of the tunnel. So.
What is the philosophical implication of finding life on Mars? One of the reasons everyone got so excited about finding water or evidence that water could have existed on Mars was because apparently water played such a crucial role in the origin of life on Earth. What is the weight of the finding? Let's say tomorrow we find out that Mars has life or had life in the past. How would that change our worldview, if at all?
Well, I think it would. And I should say that when we were first finding evidence of water on Mars in the Opportunity rover years ago, when we first had the first press conference to show what we were finding, that night I looked on all these news websites, and every one of them said, with one exception, said Mars could have supported life. And it was actually Wired magazine said Mars could have supported life, but did it? And yes, water for a rocky planet is probably a very important part of what makes a planet habitable or allows life to evolve. I think if we found that life once existed on Mars, it would have been microbial life. And certainly at the surface, it seems not have persisted. There's an ever-present community of people who thinks that Mars still might harbor life in the deep interior where there is liquid water and hydrothermal heating. Going to be a long time before we can actually test that kind of hypothesis. But I think if we found that life existed on Mars or on the planet or the moon Enceladus or Titan or something like this, it does an important thing because having two examples is infinitely better than having one. That means we know that even in our own local neighborhood, our own solar system, life evolved more than once. Now, you might say, well, maybe it evolved once and was carried by a meteorite from Earth to Mars, or actually much more likely Mars to Earth. I don't get excited about that. I know some people do. But I think just finding even a little scrappy signature of a bacterium somewhere else, immediately says, yes, life did exist in more than one place.
I can see why you don't get excited by the panspermia hypothesis, because it just pushes the question
That's right.
to another source, but we haven't answered the question. I want to zero in on one thing you mentioned, which is very interesting. You said it'll be better if we have two examples instead of one for the origin of life. As a counter to that, Nick Bostrom has put forward the thought experiment that if we do find life on Mars, it would be really bad news, that we don't want the second example. And that's because if we were to find life on Mars, that would mean that we have to update our Bayesian priors for the existence of life from 1 in a trillion planets in the observable universe all the way down to 2 out of 9 within our own solar system. So it's a massive, massive downgrade. And then that would imply, because of the Fermi paradox, because of the great silence, we've not seen life anywhere else, that it seems like if it's that easy for life to emerge, that there has to be a great filter somewhere in the future. And that means it's bad news for humanity.
Well, we're going to have to deal with whatever reality is. So I think we can get used to it. I think it is interesting that, let us say that many planets have given rise to not only life, but complex technological life. And it may be that happened 5 billion years ago on some planet in another solar system, but that planet has been dead for a long time. So the idea that you can evolve complexity, biological complexity on other planets or moons doesn't mean that all the intelligent life that ever existed is around today and they're just not, inviting us to see them. So I don't think we know. It's, again, one of the reasons why I like the idea of finding a second data point is it cuts in half the speculative possibilities, and you start having to focus on certain things. So I don't know that we're going to find evidence of past life, let alone present day life on Mars. But I think if we would, I think that would actually be a great day for humanity.
I tend to agree, but Nick Bostrom has scared me. I'm not going to lie. While we were talking about the changes between these eons, you mentioned also plate tectonics play a huge role. So let's go there. What are plate tectonics? And then what causes their movement?
Okay. Yes, plate tectonics is based on an observation, which is that features at the surface of the Earth move through time. This was first argued as a concept called continental drift back, almost 100 years ago. And people didn't like it because nobody could see how continents could move through this oceanic crust made of volcanic rocks. And so it was pretty much dismissed. And then really beginning with observations by submarines during World War II, we found out there was this big mountain chain in the middle of the Atlantic Ocean. And it was later found that was actually creating new crust, and the crust was spreading out. And that was pushing the continents apart. And that's how continental drift was born. So there are about 7 or 8 major plates on our planet and some smaller ones. There are places where new oceanic crust is forming, and that's pushing continents apart. Because we live on a sphere, that means there are places where the oceans are getting smaller and continents are coming closer together. What will happen is that the oceanic crust can actually get pushed under continents, and that forms mountains. The Andes, the Rockies, those are mountains that form when continents move over so-called subducting crust, and that then you also get mountains form when 2 continents collide, when India crashes into South Asia, building up the Himalaya and things like this. So continental drift has really given us a new, within my adult lifetime really, a new understanding of the physical features at the Earth's surface. And that has been wedded to increasingly refined work on Earth's mantle underneath the crust, where it's very clear that the mantle on geologic timescales actually circulates the materials of it. And it's that mantle circulation of warm material rising, cooler material going back down toward the bottom of the mantle again that actually drives what we see at the surface. And so plate tectonics, you're absolutely right, is a defining feature of the Earth. And I think when people start talking about how is it that life has persisted for so long on this planet, there's a place at the table for plate tectonics.
Such a massive component of the evolution of life. So the way I understand, so warm mantle rises up at the ridges and that becomes new crust. And that's happening, let's say, in the Atlantic Ocean. So it's expanding year by year, very, very slowly. And then at the Pacific Ocean side, there are these subduction zones that then move down and they, I guess, melt away as well.
Right.
So that's what's causing the volcanoes in those regions?
That's exactly right. People often talk about the ring of fire because there are volcanoes that arc all the way along, line almost the whole Pacific. And that is because crust is subducting, it's melting, and that fuels the volcanoes. Yeah.
Is that also what causes the earthquakes?
It's one of the causes of earthquakes, yeah. And again, earthquakes, by definition, reflect tectonics. Commonly, that is associated with plate tectonics. There are other things that go on. So, for example, in the United States, I think about the strongest earthquake that we have evidence of took place in the past near where St. Louis is today. That's not on a plate boundary. That's in the middle of a plate. And people are just now starting to come to a more sophisticated understanding of materials moving through the mantle that might help explain why. It's easy to explain earthquakes in Los Angeles, which is right on a plate boundary. You need things besides plate tectonics 101 to explain what went on in the past in St. Louis and other places like this. But, the good news is that again, within my lifetime, our understanding of how the Earth works has been revolutionized. It's amazing.
So what happens when there's an earthquake? What is the science behind it?
Okay, well, you have a fault, which is just where two rock masses come together. And in many cases, like in Los Angeles, the one side is moving in one direction, the other side is trying to move in the other direction. And they get locked together because of friction. And once you build up the force to overcome friction, you'll often have it give in a minute. And it's that sudden release of the friction that was holding them together that causes the movement, and that's your earthquake. And so there are various geometric variants on that, but it's largely just the differential movement of two pieces of crust that are adjacent to each other.
So the picture that I have in mind is, in a way, it's like a spring that's being loaded, and it could either be released to a small extent, that would be a smaller earthquake. Yeah. But if it's held for a long time, and if you haven't had an earthquake for a long time, that would be a massive release, and that would be a big earthquake.
That's absolutely right. And that's why people like me, when I see a small earthquake in California, I'm happy because it's doing exactly what you just said. And when things have been quiet too long, that's when you begin to worry. And we know that, I'm not an expert on this globally, but along the West Coast of the United States and Canada, there are certainly, the expectation that fairly large earthquakes will happen at least every several hundred years. So that is just, on any time scale of humanity that we can think of, earthquakes are simply part of the world you live in out there.
Okay, well, I'm not looking forward to it. What about supervolcanoes? You mentioned that volcanoes were a part of the subduction zone process where the crust, I guess, it moves down, melts, and that gets released as volcanoes. Are supervolcanoes also part of the same cycle?
They often form in a somewhat different way. And I'll call your attention to the Hawaiian Islands, which are volcanoes in the middle of the Pacific. And they're right in the middle of the Pacific plate. So they're not on a plate margin. And that really gave rise to the idea of hotspots. And that is a place where heating at the base of the mantle, right where it comes in contact with the core, causes the melting of materials that can then work its way up and have massive volcanism. So yeah, the really big, amazing volcanoes that we have seen evidence of in the past are sometimes called large igneous provinces. Again, there's been a dozen of those in the last 500 million years. They happen from time to time. I think the chances of them happening within the lifetime of you and your grandchildren are small, but they will happen again at some point, and they will wreak havoc with the planet.
Would that lead to extinction?
Depending on the size of them. And again, it is kind of interesting that when people have looked at these massive volcanic events in the past, some of them have taken place at the bottom of the oceans, and those don't seem to have made big difference to life. Some difference, but not a big difference. Whereas those that were extruded onto the surface, like these Siberian traps 252 million years ago, those are really bad news. And people have argued about precisely why that is the case. But what it says to me is there are questions of context in addition to simply the volume of material that has been extruded. And in some cases, those have, at the end of the Permian, it's thought that something like 90% of all animal species disappeared, whereas others, maybe 20% disappeared. So that's still a lot. I mean, 20% is maybe what we're thinking about over the next 50 years or so. 90% is pretty catastrophic.
Well, uplifting to think of. Well, supervolcanoes is not the only threat. I guess it's a fact at this stage that humans itself are a threat to nature and diversity with all our actions. In A Christmas Carol, Scrooge is visited by the ghost of Christmas future, who shows him a world that would exist if he doesn't change his ways. So I would love it if you can play the role of the ghost of the Christmas future today. Let's assume the year is 2050. What does Earth look like in 2050 if we don't change our ways today?
Well, that's a very good question, and one that all of us should be asking ourselves now. Again, part of my perspective comes from studying this ancient mass extinction 252 million years ago. If you ask, why did all this volcanism cause all this biological havoc? What's clear is that there was a massive rapid output of carbon dioxide. That sounds familiar. That causes global warming. A lot of that CO2 goes into the ocean, and that decreases the pH of the ocean, something called ocean acidification. Because seawater gets warmer, it can't hold as much oxygen, so it increases the area of oxygen-poor parts of the ocean. So when I look at what's happening as we speak, it is the same things that happened 252 million years ago and engendered large-scale extinctions. So in a sense, humans are causing carbon dioxide to increase at almost unprecedentedly rapid rates. What is happening right now is unusual on a geologic time scale. And we know, again, from the study of isotopes, carbon isotopes, that the main reason that CO2 is increasing is because of the burning of fossil fuels. That's not an issue anymore. We also know that Earth is getting warmer. We all know this from our personal experience, but the data bear it out. And that's an expected consequence of increasing the CO2 content of the atmosphere. I should also add that another major greenhouse gas is methane, natural gas. There's much less methane in the atmosphere than there is CO2, but on a molecule for molecule basis, it's a much stronger greenhouse gas. And again, human activities are responsible for major fluxes of methane from the Earth into the atmosphere. So we are changing the world around us. Ocean acidification, it makes, when the pH of seawater goes down, it's harder for organisms to make skeletons of calcium carbonate. And so there is, I think, a legitimate question of the extent to which tropical coral reefs will exist 100 years from now. And so I think if we do nothing, we will live in a world that is significantly warmer than it is now. That will change rainfall patterns. So some places that are agricultural centers now will not be. Some places like the Middle East, a lot of the Middle East could become essentially uninhabitable, except through massive air conditioning. And so, it's just it's a sort of very disconcerting thought of what the world will look like. And again, it's not just mere speculation that you can shrug your shoulders and dismiss. It's based on physics and chemistry that we've come to understand, and we know that these things are happening because of us. The other thing that I should say too is that there have been major dents in biological diversity and even in the population size of species that have persisted over the last 100 years. And most of those are not due to global climatic change. They're due to changes in land use, so agriculture, where there was once natural areas, overexploitation of species like animals in Africa and things like this. The human-aided movement of plants and animals from one continent to another. So you have new interactions that we haven't seen before. So I raise that just to say that, when you say that Australia has lost 10% of its mammal species and that, insect populations are down 80% in Europe over the last 50 years, that's all before global change kicks in. And so that's going to continue, but now in a world that is rapidly changing. The physical world around us is changing. So I think in the absence of concerted efforts by humans, we will lose substantial amounts of biological diversity. All the infrastructure that has been built up to deal with agriculture and things like this would have to be moved at huge expense, because the places where you can grow rice today are maybe not the same places you can grow it 100 years from now. The places where you can grow cattle today are not where you might be able to grow it 100 years from now. Sea level is going up. Again, that's measured. That's not something that we are just speculating about. And, if you live in Miami or Venice or Bangkok, that's something you should be very concerned about. And if you live in Florida and you're not concerned about it, you at least should be concerned by the fact that insurance companies are moving out of Florida. Half a dozen of them have, and more will. I just saw something the other day that suggested that, if you want to get home insurance in Florida by the end of the century, it might cost, an order of magnitude more than it does now. So basically every aspect of our lives will be impacted by this. But the good news is it doesn't have to be that way. I mean, that's what the ghost told Scrooge. And we do know that there are ways of removing CO2 from the atmosphere. There are new ways of making things like cement and building that actually use CO2 rather than generating it, which, conventional ways of making cement actually generate a fair amount of CO2. So there are things that we can do differently that will help us all. And the costs of putting those kinds of things in place, frankly, is much smaller than the costs of doing nothing. So I do think that we have the possibility of at least holding the line and possibly, improving the situation. I do actually have some faith in the ingenuity of humans. And so one can only hope that we will all have the personal and, for countries, political will to make it happen.
As the ghost of the Christmas future, just to drive the urgency, and I'm happy to hear that we can still change our ways. What's the timeline we're operating at? How much time do we have to change our ways? At what point do we go beyond the point of no return? And then let's say by 2050, within the next 20 years itself, the Earth is going to get uninhabitable if things continue the way it is?
No, I wouldn't say that.
Okay.
It's more like you're going to grow your wine grapes in Sweden rather than in France and that. But things will change. And as I say, changes that in some places may actually be good. There was an economic analysis of Europe with modeled global change, and almost all parts of Europe became worse, but Scandinavia became better. The same thing is true in North America. Same thing is true in parts of Africa, where unfortunately places that are arid now will get worse and things like that. So I would say that if we do nothing or do too little, there will be all sorts of regions of discomfort in many places. We will lose biological diversity. I don't see us being like the end of the Permian period 252 million years ago. And I think what I find interesting is that if you look at UN reports over the last 20 years, it always said, well, we need to keep global temperature rise to less than 1.5 degrees Celsius. Well, we passed that last year. Yeah. So, whether it's going to be, well, okay, now we're going to keep it under 2 and now we're going to keep it under 2.5. I don't know. I think there's every reason to believe that we can slow the rate at which things get worse. We're still some distance away from things getting better. But again, one hopes that, they always say necessity is the mother of invention, and necessity is going to be there. And fortunately, we are a species that has many, many bright, curious, talented, hardworking individuals. So I'm hopeful, but it isn't a time to sit back and let things happen without change.
How much time do we have before we change our ways? There's a doomsday clock in New York City, and that just shows 3 years left.
Yeah, well, again, the doomsday clock is an idea that goes back to when is the atom bomb going to fall again, and so we don't know. I would say that if we do nothing, you will increasingly see the problems with that in your lifetime. And this is not something that's happening 200 or 300 years from now. This is something that has already started and could accelerate or it could slow down. And whether it does one or the other has a lot to do with us. I mean, the doomsday scenarios that come from science, and again, we don't know whether they will happen, but one of the most important things for controlling climate in the Northern Hemisphere is the circulation of the Atlantic Ocean, because it carries warm waters from the equator toward the poles. In particular, there's something called the North Atlantic Drift, and this it goes up through the across the western end of the Atlantic Ocean, and it has actually been modeled that could collapse. And if that collapses, you may not want to live in Europe. Now, we don't know that it will collapse. There's a lot of argument about that, but some of the in some ways most worrisome models really do get into very serious impacts on humans, at least regionally. Again, it may be quite balmy in Toronto if that happens, but large parts of what, despite what American policy now seems to be, it does seem to be a very interconnected world. So we will all have a price to pay if we choose not to do the things that could mitigate global change.
A bleak picture, but I think it's important to paint that picture out, because I feel like a lot of people brush it under the rug and underplay the consequences of increasing carbon levels. So I'm very happy that you're able to paint that picture and create that bleak picture, because it is a pressing issue.
Well, if I could say just one more thing about that, I'm glad you brought it up, because there are, best-selling books, one called The Big Lie and things like this. And I was reading one piece of this kind of literature recently where someone pointed out correctly that there was some larger global changes, 15 million years ago than what we'll see, and that, sea level changed and, it wasn't a big deal. There were no big extinctions and that. And I said, that's right. Now let's have those changes, but let's put Miami and Venice in there. It's a very different thing. So it isn't just that this is unprecedented rates of change. It's that it's happening where our entire planet has a human infrastructure, and that makes us quite vulnerable.
Baba Diom, Senegalese forest ranger, had once said that, why do so many people care so little in the face of planetary changes that will reshape the lives of our grandchildren? In the end, we will conserve only what we love. We will love only what we understand, and we will understand only what we are taught. And I hope conversations like these and the message that you put across, it starts that process of teaching, then loving, then conserving, so that we can avoid this future that's in store for us in 2050. Before we start wrapping up, I would love it if you can tell me what masterpiece I've built with Lego. What do you think this is?
Masterpiece.
If I may say so
well,
myself.
It looks to me like a petrol station with a convenience store.
Exactly what it is.
Is that correct?
I wasn't building anything in particular, but now that you mention it, all that talk about fossil fuels, and then
there you go.
That's what it looks like. I agree with you.
You're an artist.
I didn't even know it. Final questions for you. What are some books, movies, role models that have strongly influenced you in your life?
Well, one goes back to my youth. When I was about 10 years old, an elderly neighbor gave me a book called All About Archaeology. And it just opened up a new world for me. I just loved it, still love it. And I think what its long-term significance was that I got excited about the idea that there was a history underneath your feet if you had the wit to look at it. And while that didn't directly feed into this, now I must become a paleontologist, I think it was that sense of there is history beneath our feet that had a great deal of influence. Another book that had a great deal of influence on me was a book written by the late Lynn Margulis on the origin of eukaryotic cells. Again, when I was at university, I was taking a botany course and had to do a term paper. And so I did my term paper on what was then this exciting and controversial idea put forward by Lynn that the chloroplasts of plant cells originated as once free-living cyanobacteria or photosynthetic bacteria that were captured and reduced to metabolic slavery. And I thought that was the best idea I ever heard. I still think it's the best idea.
On the origin of mitosis.
Yes.
That paper.
Exactly.
Yes. Yeah.
And when I was researching that, I learned that there was a man named Elzo Barghorn at Harvard who was finding evidence of life much deeper into Earth's history back when the events that Lynn was talking about would have taken place. And so, to my extreme good fortune, I got to work in Elzo's lab as a graduate student. And the little codicil to the story is I was sitting at my desk my first year as a graduate student, and Elzo comes in with this woman and says, Andy, I'd like you to meet Lynn Margulis.
Oh,
and to
wow.
me, that was like meeting Robert Redford or something.
Right.
And you know what? She was a kind, supportive friend for 40 years. I've always been grateful, not only for her ideas, but for her friendship. So those are at least two things that have influenced me directly. There's all sorts of, one movie I saw recently that everybody should see if they haven't, is one from, I think, the 50s called 12 Angry Men, which is about people arguing about the guilt of a juvenile murder suspect. And I think it's a beautiful lesson in learning to listen and learning to think deeply about all the evidence before you come to a conclusion. Many of us don't do that very well, but it's just, so for all your listeners, if you haven't ever seen 12 Angry Men, go see it.
I'm going to check it out. In his novel, The Glass Bead Game, Hermann Hesse wrote the following words: "Nothing is harder, yet nothing is more necessary than to speak of certain things whose existence is neither probable nor demonstrable. The very fact that serious and conscientious men treat them as existing things brings them a step closer to existence and to the possibility of being born. You've devoted your entire life to proving the existence of something that was neither probable nor demonstrable. So in light of your immense contribution to science, what would you like your legacy to be? How do you want to be remembered?"
To be honest, I mean, I've been very fortunate in science. One of the things I'm proudest of is the students and postdoctoral fellows that I've mentored. I'm very proud of the fact that a couple of months ago, I saw a list of the world's top 100 universities. And when I looked at it, I found that I had 11 former students and postdocs on the faculties of the top 10 universities. And so as I sort of get old and exit the picture, I'm very proud of the fact that people that I have helped find their own feet are the ones that are leading it in new directions. And I think more generally, I'm just glad that I was able to be part of the community. Really, I'm not working, as a lone scholar in the middle of the desert. That there's a whole community that has changed the way we think about interacting Earth and life. And that's not going to go away. And I think much of what we think about Earth's past, its present, and its future is going to come from continuing research within that context.
I think it's poetic that you're studying processes where there's a massive compounding butterfly effect, where a small change in Earth's history can have such a massive impact millions of years down the line. And I feel like your legacy, your impact is quite similar. All your contributions now, we're starting to see the postdocs emerge from that, take up faculty positions. Hopefully, they're also going to inspire more postdocs. And that's going to make an even richer legacy. So I definitely see it. I think it's poetic that your careers mirrored the work that you have done. Final question, a very easy one. What is the meaning of life? Andrew Knoll?
Was it Steven Weinberg who talked about a meaningless universe? I think each of us has to take our own sense of the meaning of life. It's not obvious to me that there is some universal meaning encoded into life and its distribution, perhaps throughout the universe. But I think that, when I look at life, I see something which, and I'm going to use the term miraculous. I don't mean it in the sense that some people might take it, but I just find the diversity of life on Earth to be wonderful and maybe improbable, certainly uplifting, certainly worth preserving. And so I think that pretty much all of us can look at life as it exists and as it could exist elsewhere and take our own lessons from it.
I think that's a great personal meaning you can derive from it. Professor, if people want to find out more, if they want to read your books, find out more about you or your work, what is the best way to find you or your work?
Well, someone once said that I was eminently Googleable.
Right.
So certainly I wrote this book, A Brief History of Earth, for the general public in the hope that people can learn more about the planet we live on. And so that's not a bad place to start. There are, if you want to dive into a more technical literature, which not everyone will, there's something called Google Scholar, and you can type my name in and see a reference, often with copies of the papers to everything I've ever written. So yeah, there's a bunch of podcasts to which this now comes to the head of the pack, but fortunately, two things happened in close proximity to one another a couple of years ago, and that is A Brief History of Earth came out, and on the same time scale, I was, to my own good fortune, awarded something called the Crawford Prize in geosciences. And because of those two things, I've probably been on more podcasts in the last 2 years than I was for the rest of my life before then. So there's a lot of ways of finding out not only what I do, but there are a lot of, we sort of live in almost a golden age of writing about natural history. Neil Shubin, Paul Falkowski, Sean Carroll, two Sean Carrolls, in fact. And so there's if you're interested in learning more about the planet you live on, there's a lot of good ways to find out.
I've always been very interested by all your podcast appearances, your lectures, and I highly recommend A Brief History of Earth. It's very well illustrated as well, and it really helps depict all these different complicated processes that happen in Earth's history and continue to happen, geological process, and really was a very insightful book for me as well. So I really recommend it. Professor, thank you so much for your time. I cannot stress how much of an honor and a privilege it was for me.
Thank you.